So welcome again, ladies and gentlemen. Our next speaker is the team leader of integration mobility of the German Aerospace Institute of Networked Energy Systems. Please welcome Dr. Michael Kröner.
Thank you very much for the kind introduction. Today I would like to talk about hydrogen quality and analysis. So the first slide is I want to introduce what actually hydrogen quality is about. This is normally purity is given by a number of contaminations, as most of you might know it, in the percentage range. This means 1 part per 100 is a different particle. And I've shown this here. You have seen hydrogen here, and somewhere in between there are different impurities, so non-hydrogen gases. And these can occur in parts per million or parts per billion. And this is important, especially in the use for fuel cell mobility or fuel cells. Impurities generally are other gases, molecules like oxygen, or it could also be water. But it's also, and I depicted it here in black, particle contaminations from abrasions from pipes, sealings, or powders from metal hydrides. So to give you a quick overview, I would like to introduce the purity grades that are typically given for hydrogen. It starts from 1.8, which is currently discussed for transportation of pure hydrogen in reused natural gas pipes, and then goes to 3.0. This equals to 99.9% purity. This can be used as fuel gas or fuel cell supply. Then there's the nominal fuel cell grade hydrogen with 3.7 quality, which means 99.97% purity. And then there are also different others like 5.0, that was actually transported and used in hydrogen refueling stations. And it's also the standard for these refueling stations. It means that 99.999 purity of hydrogen is required, and this equals to 10 parts per million impurities allowed in the hydrogen. So that's really not too much impurities allowed. And I put other stuff, as you've seen in the slide before. There was one particle, hydrogen sulfide. Sulfur components are especially problematic for the fuel cell systems because they contaminate the catalyst as they react with this particle, and then it's irreversibly contaminated, so the fuel cell loses power at that point. So that's the reason why hydrogen sulfide is only allowed in 4 parts per billion in hydrogen. That's really not much. And this is also shown here. That's the 0.004 parts per million allowed in the standard of hydrogen purity, the DIN 17124. We also have other components like nitrogen, which can be 300 parts per million. It's a typical gas that's used for purging hydrogen refueling stations during refilling. That's why I stated here. It's also the biggest part in air, so it relatively often is found in hydrogen samples. And we also have these short-term reactions, like with carbon monoxide. It can be reduced again. It can be removed again from the fuel cell system by purging with pure hydrogen. So this is not as problematic as the sulfur compounds. Yeah, and how do you measure actually this hydrogen quality? You need some special equipment. So what we use here is a high-performance gas analyzer from the company VNF. It's an ion molecule reaction mass spectrometer that can also be used together with electron impact ionization. This is a pretty sophisticated system which needs an ultra-high vacuum where you can set the conditions to be able to detect these very small amounts up to the parts per billion range of the impurities. And as it's very pure, also the measure range here is given. It's from 0 to 100 ppm, as the technical data sheet would state it. But then the question comes, what actually does 0 mean here? Because the 0 is of course not 0, but it's a limit of detection that we have to, or that we can achieve. And to go as low as possible, we therefore need a daily calibration with 8 different test gases and pretty high pure hydrogen, 6.0. So this is something we set up in the laboratory. You can see here the hydrogen bottles and the calibration gases. And yeah, so the limit of detection actually depends on your calibration gases and how good they are defined, how much uncertainties are there, and so on. So, and one information, the necessary amount of gas samples for doing this analysis according to the DIN standard, you need with this system around 10 to 15 liter of gas. And with that you can achieve values with accuracies of plus minus 2%. Yeah. So here again, I wanted to show you what the achievable limits of detection with our calibration gases are actually possible in our current setup in the lab with this machine. That's here in the middle row. You can see the standard values that are allowed and what we can achieve with our calibration gases. For water, that's for example 0.5. We do get the sulfur compounds even lower, 0.03 parts per million or 3 parts per billion. And then with this current system, we do have a small problem with carbon monoxide, which is above the limit allowed. So it's 0.2 ppm, but we can currently only measure 0.45. And I highlighted this because there's a relation with nitrogen. It's almost the same mass, and it cannot be distinguished between carbon monoxide and nitrogen, at least not with this ion molecule reaction mass spectrometer in this case. This would be better if it's combined with the electron impact ionization. And then we can also get nitrogen and carbon monoxide differentiated. Yeah. So there are different gases that have been shown. Mostly all of them can be detected. With the current system, only helium and argon are not detectable. Therefore, also this ionization mass spectrometer is needed. Yeah, and I also want to show you how we do this gas sampling. So we developed a system for taking samples at hydrogen refueling stations. That's a bit different to other systems which need a fuel cell vehicle to take the sample. So while you refuel the car, you take a sample and then you put it into a probe vessel. And here we have used a 700 bar standard tank. This is, I think, one of the the Hyundai Tucson fuel cell vehicle tanks. And with this we can use take a sample from the refueling stations up to 700 bars without a vehicle. And so this is a tank of 37 liters of volume. That means around 1.1 kilogram of hydrogen could be sampled with this system. Yeah, and we developed a specific sampling procedure for that. So I would like to show you some results from a research hydrogen refueling station, which is non-public at that time. And the first analysis we did, we saw that we had increased amounts of water inside the system. This is mainly because there was a, so we suppose it's because it's directly connected to an electrolyzer system, and there you might have some entry of water into the system. But we also found increased values of CO2 and carbon monoxide, although I explained we cannot really tell if this is a true value, but we also found a lot of nitrogen in this sample. And that's what I wanted to explain in the beginning. So nitrogen is often used to flush the system before you fill in new hydrogen. So it's likely to be found in a hydrogen refueling station. It should though not have been in there in these high amounts. So there was some problem with the purging of the refueling station. Yeah, what I also would like to show you is we are also conducting research on hydrogen salt caverns within the project HyCAV Mobil, which we do together with the EWE AG, and it's sponsored by the NOW, or the Ministry of Mobility in Germany. And there we developed a system where we can simulate the salt cavern conditions in a hydrogen test reactor, which you can see on the bottom picture. We can there produce up to 200 bar hydrogen pressure, atmosphere temperatures up to 200 degrees Celsius, and check for the materials if they have introduce impurities under these conditions into the hydrogen. But we can also, of course, look at mechanical aging under this hydrogen atmosphere. Yeah. And with this system, this can be directly connected to our gas analysis system. That means during these experiments, we can take hydrogen samples at all times and directly see whenever a reaction would occur. Yeah, and that's it. I would like to invite you to come to Hall 13, so booth B40 in this hall, if you want to have some other questions answered or want to know more about these systems. Thank you very much.
Thanks a lot, Mr. Michael Kröner. If there are any questions right now? Maybe later, then come to his booth. It's number 41, right?
Yeah, 40.
Okay.
Yeah, thank you.
So next will be an interview, and my colleague will show up soon in a few minutes. So I only can ask you to, or invite you to stay, have a drink, have a free coffee, free tea, keep seated, and let yourself surprise what comes next. It's an interview with